We'll talk extenensively about the relational model. So from now on, all the remaining topics are actually quite straightforward. If you have studied concepts like set theory, graph theory, or discrete mathematics, you shouldn't have any trouble understanding the corresponding content in discrete mathematics. For example, in our specific scenario, relational algebra is used to retrieve and manipulate fundamental operations in tuples. And each operation will involve one or more relations. When given an output, it will form a new relationship. Basically, these relational algebra operations are translated to the final SQL to perform an operation on this database. In terms of relational databases, for example, like this select, update, and so on, are all this kind of cross-join, outer join. What is it actually? It goes back to its most fundamental level. Actually, it's about relational algebra. For example, first of all is select. In reality, it is actually a symbol of sigma. It signifies that the select represents the process of inputting a relationship and outputting all tuples that satisfy a specific predicate. And this specific predicate functions as a filter. Furthermore, we have the ability to use conjunctions and logical words to enter multiple predicates. It is truly simple and straightforward, as you already know. It's quite simple, really. We are learning SQL, and generally speaking, it will be just select star from R. This R represents the original relation. And when I provide input R, it signifies that R represents a relationship. For example, within this relationship, A ID equals A2. This N is a conjunction. A logical word indicating N, such as B is greater than 102. This is a select operation. Typically, we denote projection as a pi. It essentially takes a relation as an input and output tuples that only contain specific attribute. This means that instead of using select star, which selects all tuples, projection mirrors the functionality of select, but it strictly output all tuples that include specific attributes. For instance, if I have attribute a underscore id and b underscore id, within this relation R, I set a underscore id equals to a2, that it will output. Furthermore, it allows for the reordering of attributes in the output relation. If I specify the order as b underscore id, a underscore id, then what it prints or projects in the end will be a b underscore id 102, a underscore id a2, b underscore id 103, a underscore id a2, thus performing such an operation. Essentially, this corresponds to the SQL command select attribute names from relation or table, where specific conditions are set. The union operation means that I input two relationships and output one relationship. The input relationship must have the same attribute value. So what this means is that my operation of doing a union is to find a common attribute value in the two input relationships. For example, after performing this union on R and S, it actually corresponds to combining the tuples from R and S that have the same attribute values and creating a new relationship with those combined tuples. In the database, the operation is originally select star from R, and then a corresponding operation union all select star from S is performed. And then it is combined together. And the result will be A1 101, A2 102, A3 103, and then another A3 103 because it overlaps with the previous one, essentially becoming a single data entry. Then A4 104, A5 105. This forms a new relation, which is essentially a union. And this intersection is even simpler. I need to find the intersection of R and S and input the tuples that appears in both relations into a new relation. This tuple should appear in both relation A and relation B, as well as relation R and relation S. Additionally, the input relations must have the same attributes. I'm looking for A1, but A1 isn't there. Not in A2, but A3 is present. If A3 is present, then 103 should also be present. We don't have this A4. A5 is not available, but I found A3 and 103. They appear in both R and S, and they have the same attribute. So let's find it. The new relationship is AID equals A3, and BID equals 103. In SQL, the operation would be intersect as in select star from R, intersect select star from S. This operation corresponds to finding the intersection of a relationship. There's also the difference operation. It involves inputting two relations and output a relation that includes all tuple that appears in the first relation, but not in the second. That essentially forms a complementary relation. For example, with R minus S, select star from R except select star from S. The result will be the tuples that appear in R, but not input into S. Let's find an example. If A3103 appears here, I'll remove it. Thus, the result would be A1 101, A2 102, but conversely, the operation changes. S minus R means the tuples that appears in S, but to be removed if they are also appeared in R, forming another complementary relation. So the final output will be A4 104, A5 105 appear in S, and since A3 103 is already in R, it is excluded, resulting in such an outcome. As you can see from the SQL I write, it involves an exact operation. Then there is a product operation. This is derived from the condition product, where I input two relations. It automatically output a relation that contains all possible combinations of the input tuples. What are all possible combinations? It is the multiplicative relation, where I use this relation to multiply that relation. For instance, if A111 multiplies this relation, it will perform a cross join with A313, which is this kind of multiplication relation. This kind of join connection, after initially connection, it will combine A111 with V313, the A111 with A414, and then A111 with A515. Totally 3 plus 3 times 3, which is 9 times of the tuple combinations in total. In this database, I can perform this using two operations. One is cross-join, using R cross-joins, RS. Another simpler method is select star from R, S, where the common S can integrate R and S. This output input includes all these combinations and select them out. And finally, there is a join operation. Where we talk about joins, what we are referring to is typically the natural join. A natural join actually creates a relationship of tuples. Each combination of every input relation that shares multiple common attribute values come into play. For instance, in the relations R and S, only the tuple A3103 is common in both R and S, and it shares these attribute values. Thus, automatically, we select it out using select star from our natural join S. In practice, this join operation involves inputting two relations and then outputting one relation that contains all tuples. These tuples are combinations of two tuples that shares each attribute, and the attribute values of these two tuples must be the same. Therefore, it forms a natural relationship. This join is essentially a very common operation. Typically, it involves using what we initially discussed, a foreign key, to perform a related operation through relational algebra. In summary, it is a procedural language that represents a high-level depiction of how to query, focusing more on the data model and the structure for representation. For example, if I perform an operation join R and S, whether I join R and S first and then select, or I select first and then join, both expressions will yield the same result. From a top-level design perspective, it represents a high-level query formulation. However, sometimes the order of operations can vary. For instance, performing a join up first might be very costly because it involves two full table scans to make the related connections. Then performing a select. If the select is done first, it might only need to pull one or two data points from a table, which would make the join much faster. Thus, in top-level design, we consider how this procedural language will operate, whether to make a set larger or smaller, and perform related content operation effectively. The better approach is to describe the desired outcome, and then the DBMS calculate based on this result. This capability of SQL makes it a standard in relational databases. So when mapping from SQL to how we decompose this SQL and finally operate on the disk, we also need to consider it, because as we know, disk speed is very slow. We need to thoroughly consider how to avoid this related read-write I/O issues in the design to make it more relational. That covers all the content for today's lecture. Thank you, everyone. As you all know, CnosDB Cloud is alive. And welcome to join our Discord channel, and please feel free to discuss or raise any issue if you encounter. Thank you very much. See you next time. Bye-bye.